So when we were looking at a parabola, and we noticed that the x-coordinate of the vertex of a parabola is always negative b over 2a, and we want to kind of think a little bit about how we got that number. Remember, of the vertex, let's say if I have we like function notation, f of x equals to ax squared plus bx plus c. It turned out that always our vertex is always going to be, now this gives us a parabola, of course a can't be 0. We get a vertex, the coordinate of the vertex is always negative b over 2a, comma, how do we get the y coordinate? Well, we plug it in here, negative b over 2a, the x coordinate, so it's f of negative b over 2a. Do you remember that? So where did they get this from? How do we get negative b over 2a? How come that's always the x coordinate of the vertex? Well, there's a nice way of thinking about this from what we learned before. Remember, when we had this quadratic equation, we knew our roots, remember? Which are your x-intercepts. What were the roots for this parabola? Okay, well, I guess you could put y equals 2. Well, the roots were when, well, roots are, again, x-intercepts, right? Whenever we have a parabola, these are your roots, remember? So what are the coordinates of these roots? Well, we know that it's going to be something comma 0, because y has to be 0 in order to be an x-intercept. So the y has to be 0. So what then do we then get for these x coordinates? Well, it was really we're then really looking for 0 equals 2. We were then solving, right, because we want that y to be 0, right? 0 equals ax squared plus bx plus c, right? And do you remember how we solve this? Yes, we use what's the solution for this equation, right? As soon as you plug in y equals to 0, we're looking for the x-intercept, which are the roots. Well, do we know the solution? Yeah, we do, because this is same as this is the quadratic formula, right? X equals to what? Negative b plus minus or square root of b squared minus 4ac all over 2a, right? And so those represents two roots, right? I wrote it as a plus minus, but I guess I could write it as, I could separate them. Let me do this. B minus, let me do the plus, right? So we get 2. So this, right, I guess could go here, and this one goes here, right? Those are the x-coordinates of those points, which happens to be our x-intercepts, which are your roots. Okay, so then what do we, how come, so what? Where does that negative b over 2a come from? Well, some of you kind of noticed that, wait a minute, that part, that is kind of in that quadratic formula without all these, this part, you know, negative square root of b squared minus 4ac. So yeah, that's a good observation. So where do we get that from? In order to explain that, let me show you a little graph that I drew here. As you can see, what I have here is a I drew y equals to ax squared plus bx plus c. So this represents a parabola. And I can now, nice thing about this is I could change the value of a. And as you can see, as I change the value of a, remember when it's negative, it becomes kind of goes. It becomes, remember, concaves down, or sad face. You get a sad face. If a is positive, you get a happy face. Kind of. Look what happens as you change the value of c in this ax squared plus bx c. All it does is it actually moves it up and down, right? It doesn't really change anything else, right? The shape of the parabola stays the same, but it does go up and down as you change the value of c. Let's look. If I change the value of c to 1, look, it's going to go 1 there, and it's actually that's the y-intercept. Actually, if I change it to how about -1, -2, the y-intercept of this parabola will be a -2. Of course, it doesn't always have to be where the vertex is. It could be. Look what happens as I change the value of b. The y-intercept stays the same place at -2, but it kind of moves side to side. It doesn't really get narrower or wider. It's kind of moving it to the side, kind of fixing that y-intercept at -2. So that's kind of interesting to see. So let me put that to 0 again. But what I mainly wanted you to understand is, look at this parabola. When I change the value of c, does it change where the vertex is in terms of the x-coordinate? Of course, the y-coordinate of this vertex is always changing, but notice my x-coordinate of the vertex doesn't change if I change the value of c. If I change the value of b, yeah, it does. Of course, the vertex moves. Okay, and if I change the value of a, again, the vertex doesn't move, does it? Sort of interesting. Okay, but I want you to kind of mainly focus on when I change the value of c, the vertex of the x-coordinate of the vertex doesn't move at all. So we're gonna, because we noticed that, because all it does is moves the parabola up and down, the value of c. Now let's go back to what we were looking at before. Since we noticed that, you know how we solved this equation, 0 equals to ax squared plus bx plus c? What if we were to then, because the c really didn't change the x-coordinate of the vertex, what if we solve this equation? 0 is equal to, let me do that in black, ax squared plus bx plus, instead of c, 0. So let's just solve that equation. Now this will be then a we'll still be looking for roots of this parabola, this particular parabola, when c equals to 0. But we notice that when we change the value of c, it doesn't really change the x-coordinate of my vertex. See, I can even move over here. See, my vertex, the x-coordinate of the vertex doesn't change because all it does is goes up and down. So then let me find the x-coordinate of a parabola when c happens to be 0. Okay. Now, right now, this picture, it looks like then it's going to be a 0, 0. Well, not necessarily. If b is somewhere out here or out here, right, the vertex will not always be on the origin. So this would then kind of give us an idea in terms of how to find the x-coordinate. So you see how I can, when I change the value of b, okay, my vertex would not always be at the origin, but if I go up and down, well, again, the x-coordinate of this vertex will remain the same. So noticing that, I'm going to solve this equation. Turns out this equation is a lot simpler to solve than the previous equation, because do you guys remember how to solve this quadratic equation? When c is 0, it gets really easy, because all you have to do is it's just ax squared plus bx. Well, if c is 0, don't we know how to factor this binomial when you have a common factor of x? So you get x times ax plus b. Okay, so when is this true? When would this be equal to 0? Well, this will be true when x equals to, first of all, 0. Remember, zero product property. If x is 0, the whole thing is 0. Or if what? Yes, x plus b is equal to 0. Well, okay, so we have found two roots then. So first of all, we found x equals to 0. And when would this be true? Well, let's solve for x. Ax, let's subtract b from both sides. Ax equals negative b. Divide both sides by a, so you get x equals to negative b over a. So we found our two roots, or the x-intercept, for this ax squared plus bx equals to 0 for this parabola. So the roots are 0, and so it's going to be what? The roots for this is going to be, let's write down the actual order pairs. So if x is 0, guess what? Your y is going to be also 0, because I mean, x-intercepts, right? We know y is always 0, so we found our one of the x-coordinates. So it's going to be something comma 0. What's the other one? Negative b over a. You can see this in this picture. Look, my root is here is always going to be, if I make the c equal to 0, one of my roots is always going to be a 0, 0. Isn't that kind of interesting? And of course the other one is always going to be, we now know the order pair for this one. What is that order pair? What is the order pair? It's going to be something comma 0. What's that something? It's going to be negative b over a. So this is always going to be negative p over a, as you can see. I change the value of b, and that x-intercept is always fixed. Isn't that right? Because my c is 0. So that's great. We still don't have negative p over 2a. Well, it turns out, look at where the vertex is. It's going to be always in the middle of, in between these 2 points. Is that right? At least the x-coordinate is. So remember, the axis of symmetry goes right down the middle here. Look at the x-coordinate. It's always going to be, the x-coordinate of the vertex is always going to be middle of these 2 points. Is there a way to find that x-coordinate, even if I change the value of b? What is that midpoint of these 2 points? Well, it's nothing more than the average of these 2 x-coordinates. Remember, when you find the average of 2 numbers, look, right? What's average of 0 and 2? Isn't that 2 plus 0? Isn't that 1? What's the average of 0 and 3? You can see this. Let me go down. Right? What's the average of 0 and 3? Isn't that 1.5? Right? So how do we find average of 0 and negative p over 2a? Well, you just add them together. So we were just finding the average of the x-coordinate. So you go 0 plus negative p over a, and then what? You divide it by 2. So, well, 0 plus negative p over a is easy. Negative p over a. The whole thing all over 2. What does that mean when the whole thing is over 2? The same thing as dividing by 2. So you could think of this as negative p over a divided by 2. What does it mean when you divide something by 2? That's negative p over a times 1 over 2. So therefore you got negative p over 2a. See, that is always going to be the x-coordinate of the what? Vertex. But you say, wait a minute, that's only the x-coordinate of the vertex if the parabola looks something like this. Y is equal to ax squared plus bx, and when c is 0. But turns out, even if c isn't 0, it doesn't really matter, because even if you change the value of c, so when it was 0, sure, that's what we get. When you change the value of c, guess what? The x-coordinate of the vertex does not change. So that was a nice trick for us to figure out where that x-coordinate of the vertex is when you set c equals to 0. Do you see that? Because otherwise it would be a little bit harder than this. So that's why the x-coordinate of this vertex is always going to be right in between these 2 roots, which is going to be the average of these 2 roots. And easiest way to find these roots is when c is equal to 0. So that's what we did to figure this out. So therefore, the vertex of this parabola, or any parabola, y equals to ax squared plus bx plus c, the vertex is always going to be negative p over 2a, comma, f of, if I call this f of x, f of negative p over 2a. So you just plug in whatever that negative p over 2a is into this in place of x, and you could figure out what y is. So that's how we get, that's why we get negative p over 2a as our vertex. Oops. Right here. Good.
So let's see whether we got the right vertex. So what I'm going to do then is plot that vertex. Let's go to let's plot a point, equation point. There it is. We know that our x-coordinate of the parabola, we just talked about this, it would be negative b over, I'm going to put this in parentheses, 2a. and my y is going to be f of that value. So I created a function, so it'll be, I call it parabola of negative b over 2a, and let's put a solid dot, and let's put a color, black, and let's make it big so we can see it about the size 5. Okay, see if it's there. There you go. Do you see? Now the truth test is whether when we move A, B, or C, that this stays at the right place. So let's see. If we change C, we knew it was the same. Okay, so that's what we expected. Now what happens if I change the value of B? There you go. It follows where that vertex was. So that's good. And of course, if you change value of A follows it too. Okay. Oh yeah, I earlier said when you change the value of A, the vertex doesn't change. That's not quite true. That was because it was right in this center. But yeah, when you change the value of A, the vertex does change. Okay. All right, good.